Hello everyone. My name is Owen, and today I'm going to be presenting 12314 target 8. So, like you guys just had this problem, I believe. So it says two circles have radii 25 and 12 and are internally tangent to each other at a point P. A diameter of the circle with radius 25 is drawn, tangent to the circle with radius 12 at a point Q. Let segment PQ be extended past Q to intersect the circle with radius 25 at a point R. What is QR squared? So I've just created a nice little diagram here. I put this into GeoGebra. Um, so here you can kind of see some things that like maybe if you made your own diagram that you wouldn't be able to see. So like drawing a neat diagram is definitely one of the ways that can help you get problems, especially in geometry. So you will notice that I have drawn in the centers of the circles already, even though they were never mentioned in the problem. And that's just because like with a lot of these problems that involve circles, it's just always a really good idea because often you'll have something involving the centers of the circles. Um, so first off, because like we know that Owen or P is the tangency point, it will be collinear with Owen and O2. And so from this, we have the pretty like obvious angle equality of the angle O2PQ and O1PR. And this is just because like the points are all on the same line, or Owen and O2 are on the same line as P, and Q and R and P are also collinear. Additionally, because these are circles, we have equal radii. So like, for example, O2PQ is an isosceles triangle, and the same thing with O1PR. And from that, we get some more equal angles, which are just the equal angles in those isosceles triangles. Well, actually, by putting this information together, we find that we have similar triangles, PQO2 and PRO1. And what does this tell us? Well, because PQO2, the angle, is equal to angle PRO1, we actually have that these two lines are parallel. And this is important because one piece of information that we haven't used yet is that Q is the tangency point, which implies that O2 QO1 is actually a right angle. And because we have those parallel lines, that means that QO1R is also a right angle. So now how are we going back to the problem? We want to find QR squared. So the way we can do that now is by using the Pythagorean theorem, because we know that this is just a right angle here at QONR, we can just take the sum of the squares of those two sidelines. So it's quite convenient because we already know one of them. ONR is just the radius of the big circle, which we said was 25. So ONR squared is 625. And then to find ONQ, we're going to have to do a little bit of length chasing. So if we look here at this other right triangle, O1Q, O2, we can also use the Pythagorean theorem on that triangle. So we have to find the other sidelines. So the harder one is O1, O2. So to find that, we're going to have to subtract the radii. So O1, O2 is equal to O1P minus O2P, and that's equal to 13. And O2Q is just the radius of the small circle. So that's just 12. And now using the Pythagorean theorem, this is a 5, 12, 13 right triangle. So O1Q squared is equal to 25. As our final answer, we just add the two together. 625 plus 25 is 650. All right. Yep, that's the whole problem. Thanks everybody for listening.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.